Today we're going to start a discussion about vectors, and really we've already done some of the groundwork regarding vectors in that there's a similarity between vectors and polar coordinates. So let's start with a definition. A vector is basically a quantity with magnitude, and that's a fancy name for length, and direction, which is a fancy name for an angle. So this blue guy right here is a vector. It's got a specific length, so we call that its magnitude, and from the horizontal it has a specific direction, and we call that some angle. So typically a vector is written in standard position, and that standard position is given by its relative angle measure from the horizontal pointing in the positive x-axis. And the initial starting point of the vector is always called your tail, and the ending point of a vector is called your tip. Alright? Typically we notate a vector by a variable and a, if you will, array on the top of it. So that says vector A, and it's written in terms of its length and its degree measure, which is kind of like a polar coordinate, as we already said. Now if we want to find the length of a vector out in space, we know that that vector makes a right triangle, and from that right triangle we can take the vector's x coordinate and y coordinate and use it in a Pythagorean relationship to find the length or the magnitude of that vector. This notation right here with the what almost looks like double absolute values, that is the notation for magnitude. So the magnitude of the vector is like the square root of x squared plus y squared, which again was a conversion from rectangular to polar. We know that the y value of a vector is the same thing as the magnitude times the sine of theta. So r sine theta is equal to y. That's like a conversion from polar to rectangular. And its x value, or x component as we call it, horizontal component, is given by the magnitude times the cosine of theta, which again, x equals r cosine theta is just a conversion from polar to rectangular. If we want the angle itself, that angle is the inverse tangent of y over x, which we already did in our conversions. So really nothing new, just different terminologies. So if I want to name a vector, we typically name a vector with a point, but you know that a vector is different than a point because of the notation we have here. If you look at these brackets, they look like almost inequality brackets, and whereas a point like negative 6, 2 right here is in the set of parentheses. Alright, so this is a vector in polar form given by its magnitude of 4 and its direction of 20 degrees. And rather than calling a rectangular form of a vector, we call it component form. And we write this vector's name as its actual point, negative 6 and 2, but putting it in these, if you call them inequality brackets, alright, that notates it's a vector. Also we have the variable with the little hat on top of it. Vectors in the same direction, or the same magnitude but opposite direction, can be written as having negative radii, and we also did this when we were graphing our polar coordinates. So if I have a negative vector, negative b, we just say that's the same as negative 4 and 20 degrees. We kind of multiply that through, and that's 180 degrees in the other direction. Likewise, if I have this vector here, negative 6 and 2, in the opposite direction, negative b, we take the opposite of those two lengths. Now, vectors can always be drawn anywhere in space, but typically when we want to name them, we name them by a singular coordinate relative to where the tail would be at the origin. So we actually translate these guys down. And the easiest way to do this, rather than just taking this vector and moving it down here, is to find out how far it would be down and over from the origin if this point were its origin. And to do that, we use what's called the tip minus tail method to name that vector. So once again, here's the tip, and here's the tail. So if I want to name the vector A, I basically go tip minus tail. So the tip in this case for the x is -1, and the tail for the x is -4, and then the tip for the y is 1, and the tail is +4. And when I do that subtraction, I end up with a +3 and a -3. And if I were to graph +3, -3, I'd end up with a vector pointing down in the 4th quadrant. And that's exactly where this one looks like it's pointing. So I must have done that calculation right. This guy, if I were to slide it down, seems to be pointing in the 1st quadrant. So when I do my tip minus tail, I should get what seems to be a 1st quadrant vector. So once again, tip minus tail, it's 5 minus 2 and 7 minus 2, which gives me 3 and 5. And that does look like a vector pointing in the 1st quadrant. Let's do a couple more. So here's vector C. It looks like it's pointing somewhere in the 2nd quadrant. We'll say vector C is equal to the tip minus tail. So I use my x's once again. -5 minus -3 and -8, or I'm sorry, -2 minus -8. This gets me a -2 and a +6, and -2, 6 appears to be pointing somewhere in that 2nd quadrant, so that should be okay. This guy looks like it's pointing straight down, so I better get something on the axis. Tip minus tail once again, 3 minus 3, and -6 minus -2 gives me a 0 and a -4. And 0 and -4 points right down that axis. So again, I've done that correctly. Now there are these things called scalar multiples, and in polar or in component form, what we do with a scalar multiple is we're basically taking and saying, hey, we're going to multiply your vector by a quantity. For instance, here's vector A, and if I have half of A, well, it's the same vector, but it's half the length. Or 3A would be the same vector, but 3 times its length. So relative to component form, we can see that if this vector A had a length or had a component value of 2 over and 4 up, well then 3A would be 3 times over. So instead of 2, we're at 6 over, and 3 times up instead of 4 up, we're at 12 up. And you can see that relatively easy right here. Likewise, if I have -2A, I go twice the length backwards, which is at -4, and twice the length down, which should be at -8. Now when we go to polar, again, we're looking at twice the length but the same direction. So in this case, we would have 8 and 45 degrees. Now, if we go a -A, we could say, well, we said it's in the same direction, but it's really not, because we talked about negative vectors pointing in the opposite direction. So what we could say is that would be a -8 and 45 degrees, but we know that's the same as going the opposite direction of 45 degrees, so we could say that's the same as a positive 8, and 45 plus 180, or 8 and 225 degrees. Just did an example of a component form. If we move over twice as much and up twice as much, we end up at 6 and 14. And if we go backwards the same direction and down in the same direction, we end up at -3 and -7. A lot of terminology today. That's going to do it. No Connect Ed. Just do your lesson summary, and we'll chat more tomorrow.